A very warm welcome to all of you. Myself Rajan Choudhary, Professor in the Department of Civil Engineering, Indian Institute of Technology, Guwahati, instructor for the NPTEL MOOC course Pavement Construction and Technology, funded by Ministry of Education, Government of India. Today's lecture will be the lecture 7, having the discussion over the physical and mechanical requirements of materials for granular courses under the module 3. In the previous lecture, we discussed about the characteristics of the materials which can be used in the construction of pavement subgrade, where we discussed about the different characteristics which is in terms of the Atterberg limits, liquid limit, plastic limit, plasticity index. We discussed the characteristics in terms of the determination of moisture content and the dry density relationship between the for different type of soils. We discussed about the gradation analysis. We discussed about the measurement of the strength in terms of the California bearing ratio and how it is used in the pavement design in the design of the pavement in terms of the computation of the pavement crust as per IRC 37 through the use of resilient modulus. So, these aspects we discussed for the materials to be used for subgrade construction. Today we will be discussing the characteristics of the materials which are used in unbound granular courses. At the very beginning, I would like to acknowledge the use of text, information, graphs and images sourced from various textbooks, codal standards, journal articles, reports, newsletters and public domain searches. So, when it comes to the characterization of granular course materials, there are some standard ways or standard test protocols which are followed to check the suitability of the materials to be used in the granular course construction. Now, for this particular one, the following parameters are normally evaluated, which you have the liquid limit and the plastic limit, plasticity index and the California bearing ratio. So, this particular part we already discussed when we discussed the characterization of materials for use under the subgrade construction. In addition to this particular one, granular courses have the aggregates in it. So, the aggregates, as we mentioned earlier, can be classified into coarse aggregate, fine aggregate and the finest part, which is your filler. Now, these aggregates need to be evaluated for their suitability depending upon in which course they are used. So, these certain standard test protocols are used for characterization of these particular materials to understand some of their characteristics. Now, one of that particular one is Los Angeles separation value, quite popular for determining the suitability of aggregates for used in granular bound, unbound courses, both unbound as well as bound courses. Then we have aggregate impact value, combined elongation and flakiness index, which talks about the shape of the aggregates, soundness value, which gives an idea about the weathering resistance of the aggregates, resistance of aggregates to change in different environmental and climatic or moisture related conditions, and the last one is water absorption value. Now, all these are under the classification system which is given as per IS 2386. Different parts are there for these different evaluation of different characteristics. Coming to the first characteristics, that is in terms of the abrasion resistance or the toughness of an aggregate sample. So, these two characteristics are quite important to judge the suitability of a material for use in any unbound granular courses. Now, it says it's a usual expectation that whatever aggregate we are using should be tough and resistance to withstand the degradation, breakdown of particles. And when can this happen? This can happen during the construction, that is when you are drying the aggregate, handling the aggregate. Handling means from the aggregate crushers, the stockpiles are there, from the stockpiles they are transferred to the plants. So, there the handling of the aggregates is there, then you dry them, those aggregates during the drying process. If you have to mix them with some other component, then the mixing is there, then it is again laid in the field, again graded, camber is prepared and compacted. So, during all these exercise, the aggregate should have a sufficient strength and resistance to bear these different processes from its production to finally laying and compacting in the field. So, and thereafter once construction, then the traffic loading will come over it. So, again it should be good enough or suitable enough to bear the abrasion or the wear and tear caused by the movement of the traffic. So, one is measurement of the abrasion resistance. When one is rubbed, abrasion normally comes when one is abraded, one aggregate is abraded with respect to the other aggregate. So, abrasion test is there which simulates the how the abrasion can be there in the field and gives us a measure for the abrasion resistance of a aggregate. So, abrasion test is carried out to test the hardness property of stones and to decide whether they are suitable for different road construction. These tests will give us some values for when measured through different tests, and based on these values we can convey whether this is suitable for construction in this particular layer or not. The Los Angeles abrasion test is one of the most widely used and investigated methods for assessing the aggregate toughness and abrasion resistance. Now, coming to the test procedure, which is as per IS 2386 part 4, it says that the sample which is to be tested needs to be graded, and there are in this particular case we have been given 7 grades here: A, B, C, D, E, F and G, and depending upon the sizes which are present for any particular aggregate source when used in a particular layer, we have to select the grading A or grading B where the aggregate lies in terms of its sizes. So, depending on it we can choose these different gradations. Grading A, this is weight in gram of test sample for grade. So, what if a grade 1 is to be selected, it says that in between 40 to 25 you have to take 1250 grams of aggregate. From 25 to 20 you have to take 1250, 20 to 12.5 again 1250, 12.5 to 10 again 1250. So, this gives you have to take 5 kg of material if your material falls under this particular grade for testing. Similarly, it is for B, C, different quantities are given. The grading or grading used shall be those most nearly representing the aggregate furnished for the work. So, we will choose one which is representing the aggregate in a better manner. So, if this grading A is representing our aggregate in a better manner, we will choose grading A. Now, in this test you need to have some charges to abrade, especially this abrasion reaction is created at laboratory scale with the help of some abrasive charges. I will show you in the next slide. So, how much amount of abrasive charge that are in the form of steel balls are there which are put along with these aggregate particles. So, the number of those steel balls or we can say because a steel ball used as an abrasive charge will have a standard weight. So, depending upon the number of steel balls we are going to use, the weight of the charge can be mentioned. So, it says the abrasive charge then selected depends upon the grading, what grading you are using. For that particular grading, it says number of if we are choosing A, it says number of spheres or number of balls which are to be used are 12 and which will have abrasive charge weight of around 5 kg plus minus 25 gram. So, this is again as per IS 2386 part 4. Now, once you have selected the grading, you have taken the aggregates as per that particular grading requirement. As we mentioned, we will go for say for an example, if we go for grading A, we require 5 kg of material on 4 different sieves of 1250 gram each, and the abrasive charges are to be taken around 5 kg plus minus 50 gram was there. So, then that particular aggregate sample along with that particular charge are shifted to this drum. Now, in this particular drum, it is the dimensions, the details of this particular one are available in 2386 part 4. What is important here, once we put these aggregate sample along with the charges, this aggregate drum is rotated, and it is rotated at a speed of 20 to 33 revolutions per minute, and you can see there is a shelf inside it. So there is a shelf inside this standard is cylindrical drum. So the aggregate sample along with these abrasive charges, and this is what the abrasive charge I was referring, spherical balls are there. So when these rotate, they go up to a height and then fall from that height on along with the aggregate sample. So this develops a lot of abrasive action. So and the aggregates disintegrates and reduced to certain amount of fines. Those who are resistant will get converted lesser to finer amount compared to those which are weaker in nature. So it says for grading A, B, C, D, the machine is given, and according to for the grading types, for the first 4 grading, it says 500 revolutions are to be given at this rate of around we can have 30 to 33 revolutions, and for the remaining 3 grading selections, it says 1000 revolutions have to be there. Once this part is over, then you are going to stop it, you are going to take out your aggregate sample, you are going to sieve it out from a sieve of 1.7 mm. So the material, final material will pass, whatever is retained over 1.7 mm is washed, is oven dried. So then your initial weight was there, which was oven dried initial weight, which you first inserted into this cylindrical chamber, and the other one which was retained on 1.7 mm sieve and wet washed and then dried. You subtract this one, will give you the amount which is finer than this one. So more the finer generated, weaker the aggregate is, less the fines generated, the stronger the aggregate is. So depending upon in which layer you are using, there are different percentages which is given, that the abrasion resistance it gives as the percentage in terms, the fines generated with respect to the initial weight. So the percentage wear shall be reported as the difference between the original weight and the final weight of the sample. Now in addition, here what we are experiencing, there is a fall of steel balls from a height, along with that the aggregates rub with each other. So a good amount of impact as well as abrasion is happening. There is another simple test which is known as impact test. All these tests which we normally do for this particular one major concern is these tests should be simple enough to be conducted in small laboratories, and the results should be to a good scale, should be reproducible. When you test it at different laboratories, when you test it through different laboratory personals, there should not be much variability, and you are able to capture a good feature or a good characteristics of the aggregates which will be helpful to judge their suitability in the field. So now it says the another test which is aggregate impact value, again as per IS 2386, it says this aggregate impact value gives an idea about the toughness of the aggregates, and it is a relative measure of the resistance of an aggregate to a sudden source of impact may be there, which again can be there during the production, during the transportation, during handling of the aggregates, during laying in the field, compaction, the impact forces will come over the aggregates. So it gives an idea about the resistance of the aggregate to fracture under repeated impacts. The test sample, and again now here in this particular one, there the 7 gradings were given. Here it says you take the aggregates which are passing 12.5 mm sieve and retain on a 10 mm sieve. This aggregate is taken up for doing this impact test, and we will do the oven drying of the aggregates. The oven dried aggregates are used for this particular one. Now here we will have two things. One is a measuring mold is there. In measuring mold, this oven dry aggregate is compacted in 3 layers, and each layer is given a tamping by a standard rod for 25 number of blows. So we will tamp it, will compact this aggregate in this cylinder, measuring cylinder in 3 layers, and then we will strike off whatever the surplus aggregates are there. This aggregate weight is taken up, and then this is transferred to this cylindrical test setup. Again 25 number of impacts or tamping is given by a standard tamping rod, and then this is brought in this particular setup where this measure goes here, and you are going to apply this impact load. This is a load which is raised and allowed to fall from a height of 380. So, what is done here in this particular case, you can see that there is a standard hammer weighing this particular hammer is having a weight of 13.5 to 14 kg, is raised such that its lower face is 380 mm. So, it is raised in such a manner that the lower face is around 380 mm, and then it is allowed to fall over the aggregate sample. So, we are imparting an impact load over this aggregate sample, and we give 15 such blows, and thereafter the material which is there in this particular cylindrical cup is taken out. It is sieved through 2.36 mm sieve, whatever is retained is washed, and then the weight is washed and it is oven dried again. So, we again what we are going to measure, how much fines are getting generated. During less fines will get generated if the aggregate is tough enough. If the aggregate is weak, then the more amount of fines are generated. In addition to this particular one, there are many aggregates. This we are doing on the oven dried aggregates. There are many aggregates which even become weaker when they get saturated by water, or when they remain submerged in water for a longer period of time. So, in that particular cases, before transferring it for giving that impact loads, we keep those aggregates from the measuring mold submerged in water for a period of 3 days, and then we take it out. We'll surface dry those aggregates, we'll remove the surface water, and then we will subject them to the impact loading. So, this is what the other process which is done is known as wet aggregate impact value, and what we discussed here is the aggregate impact value. So, for certain like laterite rocks are there, they become more weak when these aggregates are submerged in water. So, for certain aggregate types, you may require to measure the aggregate impact value under the wet conditions. So, especially for softer aggregates. So, now we have the material which is retained over the 2.36 mm sieve. It is wet washed and dried. So, it says the fraction retained on the sieve can be mentioned as weight C, and if the total weight, the weight which has passed through the sieve and the one which is retained, if there is a difference of more than 1 gram with the initial weight which is taken, so that means there is some loss of material which has happened. So, we will discard this particular one. The difference between the material, the sum of the material which is retained on the sieve and below that particular sieve, total should not be in a difference more than 1 gram compared to the initial weight it has taken. Now, the aggregate impact value similar to Los Angeles aberration value. B is the amount of fines which are getting generated, and A is your initial. There also what we were doing, aggregate aberration value, the amount of fines which is generated with respect to the total initial weight, and that gives you the aggregate impact value. Now, again for use in different courses, this requirement may be different. In one case it may be 24%, in other case it may be 27%, and other case may be 30%. What one can understand, as one go up means as you come closer in your material near to the surfaces where the vehicles will actually ply, you require more strong aggregates compared to when it is there in the lower layers, because the stresses gets dispersed over a wider area and the stress intensity gets reduced at lower layers. So, at lower layers you can work with aggregates having higher impact values compared to what you will require when you are using aggregates in upper courses. So, there you may require aggregates with lower impact value. Now, other important aspect which needs to be worked out for aggregates is the shape of the aggregates. Now, when these aggregates, most of the aggregates are produced from the aggregate crushers. Big rocks are crushed down to your usable sizes, and there are combination of crushers which are used to bring them from the big sizes to smaller your desired sizes. And this combination of crushers, aggregate crushers, have to work in such a manner that you get good shapes, and the preferred shape is your cubical shape, but always you will not be able to get a perfect cubical shape. So, what you prefer? You prefer to have angular and cubical aggregates. Angular, the edges are sharp enough, and if it is cubical shape is one, then it has good amount of edges. You will not prefer to have rounded aggregates, because rounded aggregates in case of road construction, especially in these granular courses, they slide over each other. There is less of internal friction which is happening between the rounded aggregates. So, that is not preferred here, especially in the granular courses or the bound courses during road construction. So, we now how to check the shape related aspects of an aggregate. One index which is used to check the shape is the flakiness and elongation index, and it is used to characterize the shape of the aggregates. Now, here two important things are taken care, that the aggregate should not be having one dimension very large compared to the other dimensions, and second is one dimension is very less, it should not have one dimension very less compared to other. So, we will say the aggregate should not be elongated one and should be flaky, very thin, because then that means there are chances that this particular aggregate, because if it is more elongated, it may break down compared to the other dimensions. If it is thin enough, then also it can break down. So, elongated aggregates, you can see this is one dimension is quite large compared to the other dimensions. These are elongated aggregate particles, these are elongated aggregate particles, and instead of them there may be other aggregate particles. Here these are thin enough, these aggregate particles are thin enough, their one dimension or their thickness, especially their thickness is quite less compared to their other dimensions. So, we will not prefer to have aggregates which are elongated. Now, which aggregate will be called as elongated, which aggregate will be called as flaky, that is the important aspect. So, here it says the flakiness of index, that is the thinness, I can say flakiness is the thinness of the aggregate, is determined in terms of the percentage by weight of particles whose least dimension is less than 0.6 times of their mean dimension. So, if I have an aggregate particle whose mean dimension normally is worked out by sieving it through two consecutive sieves. So, if I have an aggregate which is passing through 50 mm sieve and retained on 40 mm sieve, I will say that this aggregate has a mean dimension of 45 mm. Now, so any aggregate which is passing say through 50 mm and which is retained on 40 mm sieve size, 40 mm sieve size. So, in that case the mean dimension will be your 45 mm. Now, if an aggregate is to be flaky, that means if it is flaky, that for that particular case, if its one dimension is less than 0.6 times of this 45, so then this aggregate will become flaky aggregate. If one dimension of this aggregate is less than 0.6 times of its mean dimension, and mean dimension was 45. So, then this aggregate will be called as flaky aggregate. The other says, when do you call that aggregate to be elongated aggregate? So, this particular aggregate, whether it will be called as elongated or aggregate or not, then what I will check? I will first check for which particular sieve it is passing and on which particular sieve it is getting retained. So, this again, if I work out for any sieve sizes over this particular one, it may be say 12.5 mm passing and 10 mm retained, or I can say there may be 20 mm passing and 15 mm retained. So, 17.5, these are random sieves, there are standard sieves to do this particular analysis, then I will say 17.5 is my mean dimension. Now, let me say I have a same particle which is again passing through 50 mm and retained on 40 mm. So, its mean dimension is 45. Now, for any particle in this particular range, to that particle will become an elongated particle if its one dimension is more than 1.8 times of this mean dimension. So, that becomes, this shows that one dimension is extensively or is quite more compared to the other dimensions of that aggregate. Now, what is the problem which happens with these kind of aggregates? The interlocking, when these when a mix of these aggregates is prepared and when it is compacted, it is important that the aggregates roll enough and gets densely packed. But these elongated and flaky particles, they impede the compaction, they make the compaction difficult and the density is not achieved. And in some of the cases, even these particles break down because they have one dimension which is either quite less or quite big. So, these aggregates break along those dimensions. When they break along those dimensions, they raise a concern regarding the gradation, because a gradation change will be there, and second, if there is some presence of binding material over that aggregate, then there will be certain faces which will get exposed without any binding material. So, that raises concerns with regarding to the durability of those aggregate mixes also. So, it says, as compared to cubic shape aggregates, flat and elongated particles tends to lock up with adjacent aggregate particles because they lie flat on the surfaces more readily than cubical particles and resist reorientation. This is important. When the compactive effort is applied through rollers, they should reorient and get densely packed. So, they resist this reorientation to form a dense configuration. So, that is why elongated and flaky particles are not preferred. Other thing is they can break down, especially this happens more when you have open graded mixes, where more share of, as we have seen in open graded mixes, the share of these coarser aggregate particles may be around 90%. So, then there are more chances that these aggregate particles break down and during production and construction, thus affecting the gradation and durability of these mixes. So, this is an important aspect which needs to be taken care in terms of the flakiness and elongation index. Now, how it is determined? In laboratory, we have these two gauges. One is your thickness gauge. This is for your flaky particles. Now, as I mentioned, if I have an aggregate which is passing 50 mm and retained on 40 mm, so this is the range of my aggregate particle, 50 to 40 is my aggregate, this one, and so the mean dimension will be 45 mm and 0.6 of this mean dimension is my 27. So, any aggregate particle, if it passes through this particular slot, then it will be called as a flaky particle. If it does not passes through this particular one, an aggregate which is passing through 50 mm, retain on 40, if it does not passes this slot, then it is a non-flaky aggregate. Whatever it passes through it will be called as a flaky aggregate. So, this is the, so I need to do this at particular exercise for a good number of pieces to get a representative figure for it. So, I will at least go for one particular sieve sizes, here 50 to 40, or say here it is 40 to 25, 25 to 20, 20 to 16, 16 to 12.5, 12.5 to 10. So, all different sizes are mentioned. Depending upon which sizes you are using in a particular course, you can work out this particular shape, whether the aggregate particle is flaky or not. Now, once you check for this particular flaky, similarly you can check for the elongated part, but for every sieve size you have to take at least 200 pieces. This is the important aspect, because you need to have a good representation of the source, the sample which you are considering for it. The other part is when you need to check the elongation index, whether a particle is elongated or not. Then again similarly here, if it is say for 50 to 40 mm, again the mean size is 45 and 1.6 times, it is 1.6 times of it, or it is 1.8 times, no 1.6 times, it is 1.8 times, 1.8 times of the mean dimension, which will come out to be your 81. So, this, if my aggregate particle which I have chosen, if it pass through this slot, then it is non-elongated. If it does not pass, the longest dimension of it is not passing through it, if it is bigger and if it is not passing through it, then I will call that aggregate as an elongated aggregate. So, I can make a count that for a given sample of 200 pieces, how much are elongated, how much are flaky, and then if I do the I take out the percentage in a manner that this is my flaky weight of flaky particles divided by the total sample can give me flakiness index. Weight of elongated particles divided by the total weight of initial aggregates give me my elongation index. In reference to it, what we commonly used, this is one way of getting the idea about the elongated particles and flaky particles, but the index which is used or referred in our MORTH specifications for aggregates to be used in different layers says about combined elongation and flakiness index. And what it says that for determining a combined elongation and flakiness index, you will not determine separately the flakiness index and separately the elongation index, and you will not do a numerical addition of it. For this particular one, first of all, you will take an aggregate sample, that means for different sizes at least 200 pieces, which will give you a representative weight also. So, you will first do the flakiness measurement, and so through that flakiness measurement you will have flaky particles and non-flaky particles. So, that can give you the flakiness index. Flakiness index, which will be your flaky particles divided by your total particles weight. Flaky particles weight or total particles weight. Particles means aggregate here, total aggregates weight. So, you will have the flakiness index, but now for going for the elongation index, you will use the non-flaky particles only. So, once in this case it says that to determine the combined flakiness index and elongation index, flaky particles are first separated out from a representative sample and you measure the flakiness index. So, Fi is calculated as the ratio of weight of flaky particles to the total weight of the sample. From the remaining non-flaky particles, we go for the elongation measurement of the elongation index. So, this elongation index will be your your elongated particles, elongated aggregate weight divided by your non-flaky aggregate weight, because this was your initial aggregate weight which you have taken, the non-flaky aggregate only you have taken, and on the non-flaky you have done the measurement of elongation index. So, this is elongated aggregate weight divided by non-flaky. So, it says elongation index is calculated as the ratio of the weight of elongated particles to the weight of the non-flaky sample, and now this and this EI Fi value is combined to get your combined elongation and flakiness index, and then there are different requirements which have been given to control the shape of the aggregates which are to be used in different layers. So, this is an important aspect. Whenever a combined elongation and flakiness index is measured, you have to determine the elongation index over the non-flaky materials. It should not happen that you have measured your, because this is a better control over the shape compared if you do your elongation index and flakiness index separately and you combine these numerical values. So, it is always advised that this is to be taken care that your elongation index has to be determined over the non-flaky materials to get the combined elongation and flakiness index values. So, this has to be taken care when the laboratory determinations are to be done with respect to your elongation and flakiness index. Now, another important aspect which is usually carried out to judge the durability of the aggregates or their resistance towards different environmental factors, and which is in terms of soundness, and especially this is done when the aggregates have higher water absorption. So, certain aggregates, sandstones may be there, laterite rocks may be there, which have a tendency to have higher water absorption, and they may show a good disintegration, or they may break under change in the environmental conditions. So, that particular thing is usually evaluated or controlled in terms of the soundness test for aggregates carried out as per IS 2386 part 5. What it says is designed to simulate the destructive nature of environmental factors, for example, freezing and thawing and wetting and drying. in general, wetting and drying means you wet a sample, you dry that sample, wet a sample. This is called a wetting and drying. Freezing, if I put that particular one, the water enters into the pore of my aggregate particles and it is subjected to freezing. So, it is subjected to temperatures where the water freezes. When water freezes, the crystals, the ice crystals are formed, volume expansion is there. So, it will exert pressures over the walls of the aggregates, in the pores of the aggregates, and the disintegration of the rock particle may take place. So, this particular action I need to be simulated and understood through some laboratory determinations, and that is what is done under the soundness test. So, freezing and thawing are more detrimental than wetting and drying. As a result, most test procedures simulate freezing and thawing. So, at laboratory scale, the soundness test involves the determination of the resistance to disintegration of aggregates by saturated two salts are used, sodium sulfate solution is used or magnesium sulfate solutions are used to develop these crystals in these aggregates and to see how the aggregates are good enough to the change in the different environmental factors. So, this can be an aggregate which looks before it is tested for the soundness, and when these aggregates are tested with the help of these two salts, sodium sulfate salt or magnesium sulfate salt solution, later on you can see this is how the aggregates may disintegrate. So, this is important to see how good the aggregates will be there, and especially when it is checked when they have high water absorptions. Aggregate samples have high water absorptions. So, again the detailed procedure is there in 2386 part 5, but important aspect is they say how do you prepare the sodium salt solution or how do you prepare the magnesium salt solution. For that particular one, it says for a good amount of salt crystal formations, you at least take 420 gram of anhydrous salt or 1300 gram of decahydrate where sodium sulfate solution per liter of water. For this is the salt solution which is prepared. For magnesium sulfate solution, at least 1600 gram of heptahydrate salt is to be taken per liter of water. Now, in these salt solutions, what is done? These aggregates are dipped, and they are dipped for a duration of 16 to 18 hours at a temperature of 27 degree near to your ambient temperatures, and you need to ensure that these aggregates samples are well below 15 mm the top of your salt solution. So, they are kept in this salt solution for this period of time, and thereafter they are removed, allowed to drain for 15 minutes, about 15 minutes, and preheated oven, then they are again oven dried. So, this is one cycle. This is one cycle where they are submerged in it, taken out, oven dried, and depending upon the requirements, MORTH for most of the cases recommends that this needs to be subjected to 5 cycles. Considering environmental factors, people do try to do this soundness test for more number of cycles also, but the MORTH recommends at least 5 number of cycles have to be done for this immersion and drying with these salt solutions. And then again, what is done here? The loss of weight is measured. How much loss of weight is there once the sample is oven dried? When it is sieved, more loss of sample is there, that means the aggregate is weak enough, it is less durable, and if less, and the requirement is also different when sodium sulfate salt is used and when magnesium sulfate salt is used. So, depending upon the use in different courses, these requirements are given, what value of the soundness have to be there when sodium sulfate salt solution is used or when your magnesium sulfate salt solution is used, and for how many number of cycles which are there. 5 cycles are the standard cycles which are given by as recommended by MORTH specifications. Now, let us come and see, we just discussed briefly some of the common tests which are to be done on materials used in different layers. We will now see what are the requirements of those test values in different courses. So, here you can see this is granular sub-base course material requirements. Now, first of all, it says what material can be used. Now, we already discussed that this granular sub-base course can be constructed in one or more layers, and if one or more layers, there will be a lower subbase and an upper subbase will be there, and it can be constructed in one layer also. What materials can be used in it? It says that for the granular course you can use natural sand, crushed gravel, crushed stone, crushed slag, or a combination of these particular ones, depending upon the availability of the material in that region nearby that construction site. A combination of these can be used. Now, certain materials like brick, concrete and crushed concrete, which may be locally available, are preferred for use in the lower subbase layers specifically. And whenever these are, you can see this is how a natural sand is there, this is a crushed slag, this is what you get from aggregate crushers, crushed stone is there. You will always try to see that there is no other organic matter which is present in this particular one. Now, what are the requirements which are there? It says that in addition to the physical requirements given in the table below, this is the table which is given by MORTS 2013 for the materials to be used in granular subbase course. It says that as I mentioned, that the aggregate impact value can be, a maximum value can be 40%. So, only 40% fines can get generated. Maximum value is 40%. When it comes to liquid limit and plasticity index, it says that the liquid limit should be less than. Higher the liquid limit, a general conception is it makes your material to be more towards a plastic nature. So, a liquid limit of a maximum value of 25% is allowed for this particular one, and a plasticity index again maximum 6% is allowed. In addition to this particular one, it says that when you measure, as we discussed in the previous lecture, that the CBR is to be determined at certain percentage. When we were looking for subgrade, it has to be determined. The CBR specimens have to be compacted at 97% of the maximum dry density. Here it says the CBR is to be determined by compacting it to 98% of their dry density, and this CBR should at least have a value which should be more than 30%. So, the strength in terms of CBR should be more than 30%. So, these are the requirements which are given. So, it makes use of your aggregate impact value, and it says that soft aggregates like concrete, brick, ballast and laterite shall also be tested for wet aggregate impact value. As I said, this needs to be ensured. What is the wet aggregate impact value? Because certain aggregates becomes significantly weak in the presence of water. They may perform good when they are tested in dry condition, but when they are tested under wet condition, so that is why we discussed that wet aggregate impact value also may be required, especially when the aggregates have water absorption more than 2%. So, it says that is given below, and if the water absorption when determined as per this is found to be greater, the aggregate shall also be tested for wet aggregate impact value. So, this is for the aggregates to be used in granular courses. Now, in granular courses there was another mix which we discussed was the waterborne macadam. So, this waterborne macadam most of the time preferred to be used as a granular base course, or sometimes it can be used in upper layer of your subbase course also. So, here again the requirement says what materials can be used for this one. Crushed or broken stone, crushed slags, overbent brick aggregates can be used. So, there are like you have Mizoram is there where a good amount of this brick aggregates are used in different construction applications. And then you can use any other naturally occurring materials such as concrete and laterite to be used, and all have to be checked for their suitability. Now, what it says that materials other than crushed or broken stone and crushed slag shall be used in subbase courses only if this waterborne macadam is used as a subbase course. If crushed slag gravel is used, not less than. Now, what is this? This gravel and crushed shingles, even the riverbed material is normally crushed. So, when you are crushing it, these gravels, it says that 90% by weight of the gravel shingle pieces retained on 4.75 shall have at least 2 fractured faces. Now, what is this fractured faces? If I get an aggregate from a riverbed, it can be a rounded aggregate. Now, if I break these aggregates at this particular edge, So, I'll create some projected area. There will be this face will be generated. Now, this is the face which has been formed when I have broken this particular aggregate. So, this is, and there is another area which is the projected total area of this one. So, if one face can be called, there may be, if this is an rounded aggregate, there may be one face, maybe this part may be chipped off. So, one face is created as here, this one also, whether this can be called as a fractured face, or if I need to say a small, this one is there, this kind of shape is there. So, the entire one went away. So, whether this here this one is there, whether this can be this face can be considered as a fractured face or not. So, the important aspect, it says any face which can be considered as a fractured face should have at least 1/4 of the projected area, 1/4, this area of the fractured face should be 1/4 of its total projected area. So, it says that the maximum particle cross sectional area should be, and the one which is there with this fractured face should be at least 1/4 of this total projected area. Then only, and there should be this sharp edges should be there, then only this face can be called as a fractured face. So, this is very important when we break down the riverbed material which are rounded and we use them into different courses. So, when you are using in waterborne macadam, you need to ensure that 90% by weight of this particular one should have at least 2 fractured faces, and one fractured face will be considered only if it has a projected area 1/4 of the total projected area of that aggregate. Now, again, as there is a requirement which is given for the aggregates to be used as waterborne macadam, Los Angeles aberration value 40%, aggregate impact value 30%. As I mentioned, when it was there for granular subbase course in the previous slide, it was 40%, here is it 30%. Here it gives the requirement of combined elongation and flakiness index. This is very, very important. You need to check it is a requirement of elongation and flakiness index separately or a combined elongation and flakiness index, and here it restricts a maximum value of 35%. And this says that if the aggregates get softened in the presence of water, go for wet impact value, and along with this specifically it says that flakiness and elongation index is enforced only in the case of crushed broken stone. When you are breaking, because these are industrial waste products or riverbed material, when you are breaking it, crushing it, so they have a tendency to be more of rounded shapes are there. So, if you are breaking it, you need to ensure it for the shape, especially the shape part, that flakiness and elongation index is ensured. In case of waterborne macadam, the requirements in respect of Los Angeles, and if I am using this, as I mentioned, this can be used in sub-base courses. If I am using waterborne macadam in sub-base courses, the requirements of Los Angeles aberration value and aggregate impact value will become 50 and 40%, because 40% what was there in case of the granular sub-base courses. So, if this material is used in sub-base courses, instead the aggregate impact value requirement will be 40%. So, all these things needs to be taken care. Now, the other, since during the waterborne macadam construction, we have seen you need to apply the screening material and then you need to apply the binding material. So, there are also certain requirements is there what is to be considered for the screening materials. So, the screenings to fill in the voids of shell generally consist of the same material as the coarse aggregate. This is one important requirement. Second, it says non-plastic materials such as muram or gravel other than rounded riverborne material can be used, but it says that this should be non-plastic material. Now, for making it non-plastic, it says that the liquid limit and plasticity index of this material should be less than 20, liquid limit should be less than 20 and plasticity index should be less than 6 for any material to be used in screening, and the fraction passing the 75 microns should not exceed 10%. So, if you are using waterborne macadam, the screening material needs to be ensured for the liquid limit, plasticity index and the percentage which is passing the 75 micron sieve size. In addition to that, when the binding material is used, once the screenings are used, and here you can see a WBM construction which is going on, waterborne macadam construction which is going on. If this particular layer, when you are using a binding material for a WMM layer as a filler material, then again it says a suitable material, but the plasticity index of this material should also be less than 6. So, we have seen when coarse aggregate particles are there, requirements of Los Angeles aberration value, requirement of impact value is there, requirement of fractured faces is there, requirement of flakiness and elongation index is there, requirement of, if the water absorption of more than 2% was there, requirement of wet aggregate impact value is there. In addition to that particular one, for finer proportions, there is requirement with respect to the liquid limit, with respect to the plasticity index, and with respect to the material which is finer than your 75 micron sieve size. So, these are important considerations for different materials to be used in different courses. The other granular unbound course which is used in the construction of flexible pavement is your wet mix macadam. Now, this is used as a base course. So, the requirements should be more stricter compared to what the requirements we have seen for sub base courses. Here you can see that where the aggregate impact requirement for granular sub base courses was 40%, here it is 30%. So, this is another part. Second is Los Angeles aberration value, it says it should be 40%. If an option is given, here it is, you can see here it is mentioned, or you can do a Los Angeles aberration value or an aggregate impact value. It is preferred to go for Los Angeles aberration value if the water absorption is not more than 2%. If you are finding there are certain aggregates which are showing higher water absorption, then aggregate impact value, especially wet aggregate impact value, could be quite useful. Otherwise, if the water absorption are within the limits, a Los Angeles aberration value test is more preferred because it in some manner gives the abrasive as well as the impact forces during its measurement. So, this can be preferred if the water absorption is not more than 2%. Then there is this combined elongation and flakiness index for the material to be used in the wet mix macadam, which is used as your base courses, and it says that the requirement should be less than, the combined elongation and flakiness index should be less than 35%. And what materials can be used? The most preferred is crushed stone aggregates. If crushed, again it says crushed gravel and shingles is used, not less than 90% by weight of the shell have retained on 4.7 have shed at least 2 fractured faces. Again, this important requirement is there when you are using, when you are crushing it, because the shingles, the gravels, they need to be crushed down. When you are crushing them down, it is important how many, when it is done at aggregate crushers from the natural rocks, good amount of crushed faces are generated. But when it is done for these shingles, slags, then you need to ensure that good number of fractured faces are generated, and here it says 90% of the aggregates by weight should have at least 2 fractured faces, and this is tested for the material above 4.75 mm of sieve size. And the other requirement, as mentioned, that if they have water absorption more than 2%, then we again need to go, here it says in addition to wet impact value, it is preferred to go for the soundness test. So, that soundness test can be done because water absorption may be more, the aggregate may be more susceptible to degradation under your freezing and thawing conditions. So, you will try to ensure your aggregate suitability through soundness test also. So, when these aggregates are having more water absorption and more than 2% and to be used as a wet mix macadam in the construction of your, this is a base course construction, a paver is used for laying the wet mix macadam layer and compaction. We will discuss more about them when we will discuss about the construction aspects. So, if more than 2% of water absorption is there, you can go for aggregate wet impact aggregate value. Along with it, it has to be checked for your soundness test to ensure that it is durable enough. So, this completes the discussion, especially in terms of the requirement of the materials to be used in your granular courses. Thank you.